Let's look at this next problem to express 22 to the 2222nd power divided by 5 to the 5555th power in scientific notation accurate to 6 significant figures. To do this, first we note I just have a TI-83 plus on the screen right now. Let's try to do it the old-fashioned way. 22 to raise the 2222nd divided by 5 to the 5555th. And the calculator doesn't like it. Overflow. The numbers are simply too big for the calculator to handle. Now this is simply unacceptable. I mean, there is a number, it is, and the question is, what is it? And it's not acceptable that the calculator can't do it. You might have a calculator that is able to handle this, but the TI-83 Plus certainly cannot. So what do? The way that we're going to do this is basically do it the old-fashioned way that folks did this a generation ago. Certainly the way that I would have done a problem like this back when I was taking pre-calculus, and that is to use logarithms. So let a be equal to 22 to the 2222nd divided by 5 to the 5555th. Now let's take the logarithm of both sides, and by tradition only, let's take the logarithm base a base 10. And we're going to use logarithm base 10 because we're going to write this in scientific notation at the end. On the right-hand side, we will have 2,222 times the logarithm base 10 of 22 minus 5,555 times the logarithm of base 5, or logarithm of 5 base 10, just simply using the laws of logarithms. Now these numbers are significantly smaller than the numbers that appeared on the line before, and so the calculator can handle these. So 2,002, well, let me clear the screen. 2,222 times the logarithm of 22 minus 5,555 times the logarithm of 5. This works out to be negative 899.915. And I'll keep writing out the places. 1773. And so therefore A itself is equal to 10 to that, 10 to the minus 899.915 1773. Okay, so let's try that as our answer. 10 raised to that number. Well, 0. That's not very helpful. It's obviously a very small number, but it is not identically equal to 0. So the way that we're going to get around this is as follows. We need to have 10 to an integer and then a positive part. So because I have a negative number here, and only because I have a negative number here, let me write this as 10 to the negative 900 times 10 to something else. Now the something else would be 900 minus 899 point and so on. So 900 minus 899.9151773. So 10 to the 0.0848227. Now this is almost in scientific notation. I have 10 to an integer, negative 900, and the thing that's multiplying it is going to be between 1 and 10. 10 to the 0 is 1, 10 to the first is 10, so 10 to the 0.08, whatever that is, that's between 1 and 10 someplace. So to finish the problem off, 10 raised to the thing that we just figured out is 1.21, so 1.215689596, more than that in a second, times 10 to the negative 900 power. Okay, and so basically that's our answer. Now I shouldn't care. I really shouldn't have carried so many decimal places. Here I had 1, 2, 3, 4, 5, 6, 7 significant digits here. And so this is probably only good to 1, 2, 3, 4, 5, 6, 7 significant digits. So up to here we're probably good. But the other digits here certainly are questionable. So let me leave this on screen, but let me underline in green that I'm not so sure about those digits because I only had actually I only had 6 significant digits here, and so I'm not so sure about the numbers that are appearing in green here. I am pretty sure about the 1, 2, 3, 4, 5, 6 digits that appear here, but not necessarily the ones in green. Those may not be exactly correct. To get a closer look to see how accurate this indeed worked out to be, let me pull up Mathematica. So 22 raised to the 2,222nd divided by 5 over 5 to the 5,500, 5 to the 5,555th. And Mathematica will do this exactly. So there's your numerator all the way to here. And starting on the 6, there's your denominator. That's pretty long, but that is exactly correct. Let's evaluate this to, let's say, 10 decimal places. And we get 1.21568597. So it looks like, except for the last digit here, we've got the digits correct. So that's kind of a lucky coincidence as opposed to something that you can expect to happen all the time. But looks like that we have the correct answer using logarithms that we got by brute force from Mathematica. In closing, I wanted to point out that the step that we did here of going from negative 899 to negative 900 is something that we only did because we had negative numbers. If the number here had been positive, if it had been positive 899, then I would have wanted positive 899 here, and then the decimal part would have simply fallen on the next line. The idea is that this number here that I'm underlining in blue, I'm just going to try and underline in blue. The idea is that number that I'm underlining in blue must be between 0 and 1, so that 10 to that must be between 1 and 10. And that occurs when, if this was plus 899, then I would have plus 899 here. Because this was negative 899, I went down to negative 900, so that I'd have a positive number that's been underlined in blue here. So that's just a quick comment about how to do a problem like this. This is basically old school using logarithms. Back in my day, we used log tables to actually do the logarithms as opposed to calculators. But this is basically the technique for being able to do a computation like this, even though the calculator can't handle it directly.